Yeah, the solvent has nothing to do with the reaction.
How is that occurring then?
The electrons are attacking the bromine. Pi bond is source of reactivity. Electrons are not held that tightly. Pi bond electrons will react with electrons.
But the bromine is
Schizophrenic.
negative, right?
Schizophrenic. Okay, bromine is formally a nonpolar molecule, but it's easily polarizable.
Okay.
Easily polarizable. And we have a handout here. One handout all the way around. Easily polarizable. Nomenclature. Outline. Mechanisms. And we're looking at halogenation. THC, yeah, how do we do on that? Put the answer key out, yeah? Obviously, nothing's happening up here. Chemistry's going on right here, yeah? Acid catalyst. The only reaction you know right now is the reaction of an alkene with H+, right? You got to recognize that's what you know. Okay? You got H+, do you have an alkene? Yes, right here. Where are you going to make cation at? Left or right? That's the question. What can attack the cation? Well, what needs to attack the cation? How are we doing on that so far? Okay, anti-addition of halogens to alkenes. We introduced this before. Chlorine or bromine, schizophrenic. Okay, the pi electrons will attack the halogen, attack one, keep the other off. Chlorine or bromine not ionic, they're covalent. So we cannot show Cl plus, Cl minus. Okay? Where are we going to make cation at? Left or right? Left. Cation here. Okay? But hold on. Are we under letter B, which says no carbocations? Mechanisms without carbocations? Why am I showing one? That's because I think it's helpful to do this, because it reinforces where carbocation would be. I think it's the best way to show it. But we have to understand that this is not really formed in real life. And I say NAF, not actually formed. It's not an intermediate. That's Stevens and me recommending to you to draw this on your paper to help you understand this. But you got to understand it's not really formed. What happens next, though? We form Cl minus there. When we take that off, it became the fourth lone pair. You got to see that. But there's also a new Cl that we just attacked, and we make this bond. Something attacks here. Which one's closer? Slap my hand. You didn't even move. I'm so fast here because I'm right here. B is going to attack. I call that back bonding. Nobody else does. Okay? These two reactions happen at the same exact time. They're concerted. Okay? Same exact time. Can y'all hold hands or something? You're bromine or chlorine. Pi bond. Y'all are schizophrenic. Back and forth. Ooh, polarized. Okay? Somehow. You're interacting with oxygen. Oxygen polarizes you. Somehow it gets polarized. And physics takes over. Electrons. Ooh. I'm going to go make a bond. And when I come here, I'm going to push you off. Okay? I'm going to push you off. You become Cl minus. You like being minus. Right? Okay? I make bond. But guess what? As soon as this bond's made, this hand's coming here. Make bond here. Bam. It's just one transition state. One transition state, and there you go. Both of these steps happen at the same time. Concerted. That's what concerted means. Same time. Now, books will show this. Arrow here, and arrow here. I just think that's too much. And students, I don't, okay? Carbocation, this is the way I do it. Nobody else is going to do it like this. If you show this, you need to write NAF. Because if you don't write NAF, it appears that you're saying that this is an actual intermediate. Not an intermediate. Here's your first intermediate, and actually only intermediate. First and only. Okay? called a chloronium ion. It's a bridge, three-membered ring, bridge, called the chlorine, made a bridge back over here. Positive chlorine, which looks odd. From there, the other chloride, which did not do that, no aid, no aid, it attacks here. And these electrons make bond here and kick that chlorine back off. And gives it back its lone pair. And what does all this give? Well, that gives final product. Because that chlorine now has 3 lone pairs. And this chlorine has 3 lone pairs. Because the 4th lone pair made bond. And we're going to call that backside attack. Because here, we're making a nucleophile to carbon bond, but we're kicking off something. And we showed that over here on the very important green sheet, 2 ways to make nucleophile carbon bonds. And the second way was a nucleophile to attack a carbon and kick something off. And that something that gets kicked off is called a leaving group. And whenever you do this, the nucleophile attacks the carbon from the side directly opposite the leading group. It's called backside attack. Backside attack. Okay? And I told you this page right here is hugely important. 2 ways to attack. Okay? And it's called backside attack, and this will become more relevant on the next page. Or you call it opposite side attack. Question, why does it attack this carbon and kick the chlorine off of that carbon? Why not attack this carbon and kick the chlorine off of that one? Well, that's because there's more partial plus here. Why is there a partial plus? Well, chlorine's electronegative and it's pulling. And you imagine a regular chlorine pulling. This is a positive chlorine. It's really pulling. A positive chlorine is mad. Chlorine doesn't like being positive. Well, it can also pull here, right? Can it pull on that carbon? Yeah. Well, which ones are going to pull more on? The answer is this one. Why? Because this one has 2 rich friends. It's like it's stealing money. Okay? Borrowing money. Who are you going to borrow more money from? A friend of yours who has 2 rich friends, they have 2 rich friends, or a friend of you that's kind of broke? Which one are you going to borrow more money from? The friend that has a couple of rich friends, like rich parents. How about that? This friend has 2 rich parents. That friend don't have any, okay, all right. The chlorine can steal more electrons there, and it thus does. And so this is it. This is a larger dipole over here. And you end up attacking the more substituted carbon. Guess what, though? It's the same carbon that we formed carbocation on. It's going to attack that same carbon, which is why I like to show that. But guess what? It doesn't attack a free carbocation. Instead of attacking a free carbocation, it attacks a carbon that was back bonded to, and then it kicks that chlorine back off. And that's important from the stereochemistry. Because 2 different ways. If we attacked a free carbocation, which side would you attack from? Here we go. Here's carbocation floating around. Which side are you going to attack from? You attack from that side. Reasonable, because you're over there. Which side are you going to attack from? That side. Reasonable, because you're over there. And you get both. Right? How do you attack a carbon when you kick something off? Backside. And I refer to that very important page over there. 2 different ways, 2 different stereochemical outcomes. And if you learn that right now, you'll be good to go the rest of organic 1 and organic 2. Okay? I've seen some students who go through organic chemistry and never understand the two different ways to attack the carbon. And thus, the whole time it was trouble along the way. Guess what? When we get to test 3, 2 different ways to attack carbon, it's going to be all over the place. But you want to learn it right now and understand it. Okay? It's kind of like me telling you, hey, you got to know 2 plus 2 is 4 and 4 plus 4 is 8. And if when we move on to algebra, if you can't do that, you're going to be in trouble. And then you never learning that 2 plus 2 is 4, and then you can't do algebra. Okay? Please learn that page, understand the stereochemistry. All right? Which is more likely? Over here, that's what we explained. You get more partial plus on that carbon because the chlorine is going to pull. Does chlorine like to... Why did chlorine make this bond? Anybody wonder about that? Why did chlorine do this and become positive chlorine? That's not good, is it? And also a 3-membered ring. That's not good, is it? So why would that chlorine back bond? Well, the answer is it's a bond. And bonds are good. Even though it's a positive chlorine and a ring, we still got a covalent bond when it's back bonded. And guess what? You can't help physics because what's the charge of electrons?
Negative.
And what's this charge?
Positive.
And are they going to attract? Yes. How much do they attract? Is it a full covalent bond or is it a very polarized covalent bond?
Polarized.
It's polarized. Which way is it going to polarize? This way or this way? The way which we said, this way. More partial here because it's got 2 rich pairs. Okay? So why don't we just show it like this all the time? Because partial bonds are a little cumbersome to show. It's back bonded. We got to know that it's polarized. That's why when we show HCl, everybody fine with showing it like that?
Yes.
But you really know that that bond is very polar, isn't it? Or do you always want to show it like this? Okay? It's very simplistic, but we got to understand what's there. Question?
Why does the negative chlorine not get attracted to the positive chlorine since it's more positive than just the partial positive carbon? Like what keeps the 2 chlorines from coming
Why are you
back
saying this
together?
is more positive than the partial positive carbon? This is actually more correct. Because that chlorine, it back bonds. Here we go.
Right.
We just got here, and you're plus. I'm chlorine. Okay. Ooh, plus. I'm minus. Back bonding. But how strong? Does the chlorine come in here and make a strong bond? No, it doesn't want to make 3-member ring and be positive. So what does it do instead? I'll make a pinky bond. Okay? Because I don't want to strain too much. I don't want to take home too positive. So you see this pinky bond that's really made? It's a light bond back here. It's partial plus. Here's another answer. If this attacked that, what would you get? What would be the problem? It would be chlorine here, and you're going to bond another chlorine here. And now we got what? What's the charge of this chlorine? 2 lone pairs. If this made bond to there,
1 lone pair.
no, there's 2 here. If this just made a bond here, there's still 2 lone pairs there, right? One doesn't disappear. You're thinking that would be the problem?
Yeah, why doesn't it do that? Is it just because then
Because
you
this is a
recharge it?
nasty looking chlorine.
Okay. Because that's real.
And also the 3-membered
Oh, I see.
ring is still here.
Yeah, there's too many.
3-membered ring, ugly looking chlorine, meaning very high energy.
Yeah.
It's a very high energy product. And very high energy products typically going to have very high transition states leading to them.
Okay.
Much better for it to attack here and to push that off. What do we get? No ring, chlorines look standard. And here's the other thing. We know when you do this reaction, you get the product like that. we don't get this thing. So we're showing a mechanism to get the things that we know we get, which has been proven in other ways. Okay, this is mechanism. Predict product. Okay, in terms of predicting product, it's pretty darn easy reaction here. Alkene, bromine, what do? We stick a bromine on each carbon, yes? That's what we did above. We stick a chlorine on each carbon. All right? And if you don't have any stereochemistry, it's pretty darn easy, and the product would be boom, boom, boom. Okay, put a bromine here, and put a bromine here. And there you go, there's your product. You got no mechanism. And the mechanism is much more involved than that. We put a chlorine on each carbon of the alkene up there. What type of stereochemistry do we have here? We have one chiral carbon, and you can star that one for future reference. Okay? Do we have to worry about regiochemistry? Instead of putting bromine here and bromine there, would you rather put bromine here and bromine here? You have no regiochemistry. You see, if it was HBr, you would say HBr here, or Br here, H here. If you reverse these, it's the same thing. So there is no regiochemistry. But there is regiochemistry here. This is an interhalogen. They're rare, but it's possible. Now, this doesn't have to be schizophrenic because we know that chlorine is more electronegative, and the iodine is partial plus, and the chlorine is partial minus. It's currently polarized. Now, here we have regiochemistry, and what's going to be the product here? Well, think mechanistically. Pi bond attacks one. Which one's it going to attack? The electrons are going to attack which one?
Iodine.
The iodine. Where are you going to leave cation at, right or left? Left. These attack iodine and kick off the chlorine. Up there, we attack chlorine and kicked off chlorine. What does that give? Boom, boom, boom. You bind to iodine. What's here? Carbocation plus what? Cl minus? Do you think that's really formed in our mechanism? Same as above. The answer is what? Not actually formed. Why not? Because this new thing over here has a lone pair, and the lone pair is going to back bond. And guess what? As soon as this attacks, this lone pair is back bonded. It's concerted. All right, we said that. And so the first intermediate looks like this back bonds to that carbon, two lone pairs. The iodine is positive here. When the chloride comes in here and attacks and pushes the iodine back off, which carbon will it attack? The answer is the same one as your carbocation. All right? Because this has a rich friend. All right? More partial can build up here. Plus. Cl minus attacks here. Yes, it's backside, but we're not really showing any stereochemistry yet. Attack, kick it off. And what's the product? Iodine there and Cl here. We can put lone pairs there. So the question is, which carbon is the iodine going to be on? One on the end. Right? So the mechanism shows you where it's going to be. So the iodine is what gets attacked. The Cl minus is what comes in next. here's your only intermediate, iodonium ion. Just because this came up here doesn't mean I can't draw the chlorine down. This is making a bond to that carbon. There it is, it's bonded to that carbon. That is chiral. And we'll talk about that more going forward. Okay, this reaction is typically just bromine and chlorine. F2, it's too reactive and you're going to get explosions a lot of time. And iodine is too unreactive. Actually, if you just use I2, the reaction tends to want to go in the reverse direction. So bromine and chlorine are the most common for doing this halogenation of the alkenes. Question?
Are you saying that iodine is attacked first because it's more positive than chlorine?
The electrons of the alkene are more attracted to electrons are attracted to positive.
Okay, not because of its orientation, because you could just flip it, obviously, right?
But what?
Like, you could just say CLI. So it has nothing to do with the order in which it's written. It's more so the chlorine is more electronegative, and you would want it to be on the
dipole
positive.
here. This thing is polarized.
Right.
Which end is partial plus? Which halogen is partial plus?
Iodine?
Yeah.
Okay.
So that's the one that we say is electrophilic.
Right.
It likes electrons. It likes electrons to attack it. Okay? You need to know what an electrophile is and what a nucleophile is. Those are just fancy words for what they like to attack in terms of charges. It can either be a formal charge or it can be a dipole charge, a partial charge. Question?
Since the first one is bromine and bromine, does it not do the ring thing? Where like, do you know how the I did a partial bond to
the first with bromine?
Yes.
A bromonium ion.
No, does it like do the ring thing? The second one does.
What do you mean ring thing?
Like how they made, yeah.
Yeah, the first one is bromonium ion. Chloronium ion, bromonium ion, iodonium ion. Yeah. What do you ask? It's the same mechanism for all of them.
I was just wondering.
I didn't do mechanism for a second one, I just showed product. Okay? There's a mechanism for it. Okay? Okay, how do we know it is, this is a trans addition of X2 to alkenes. How do we know it does not involve a carbocation? Well, we already kind of explained it. It has to do with the attack and the outcome. But also we know this. If you take this cyclohexene and react it with chlorine, we'll add 2 chlorines to each carbon, but they will only be in a trans orientation to each other. Do this flat. You only get trans. You do not get the cis product. Okay? Thus we can say the reaction is stereoselective. Because these are stereoisomers, right? And you only get this stereoisomer. So we selected for one stereoisomer. Now, more specifically, we selected for a diastereomer. We'll be able to discuss that more later. Now think about this. If the reaction involved, okay, we attack here, we're going to make cation. It doesn't matter. It's symmetrical. Top or bottom's the same. Carbocation. All right? Well, let's don't do any backbind. Let's say this is really formed. And then Cl minus attacks. What would the outcome be in terms of stereochemistry? How do you attack a carbocation? Which side?
The backs. Or
Which side do you
whatever's
attack
closer.
carbocation?
Whatever's closer.
Doesn't matter.
Whatever's closer.
Either side. Okay? And so, if you had this, by the way, when this bond is made, that bond is now, this carbon is now tetrahedral, yeah? There's an H there. So that new bond has to be either forward or back. I'm drawing it forward there. But if it's forward, and the Cl minus attacks either side, the Cl new bond can either be forward or it can be back, right? That'd be either side, forward or back. Well, if it did that, this would be cis, and this would be trans, right? But we know you don't get any cis. So that mechanism makes no sense. You can't show a mechanism that doesn't. How would you explain that you only get trans? You'd have to say that the chloride only attacks from the back. That makes no sense because we know that carbocation is attacked from either side. So you have to scratch your head and say, well, maybe there is no carbocation. Maybe there's another mechanism. And by the way, when you attack this chlorine, the first new bond can either be back, forward, or back. But if this is back and the other one comes in either way, you would have front back or you would have back back. And you get the same thing. Again, you would be getting cis, but we know you don't get any cis. Why do we only get trans? Because this doesn't happen. Instead of that attacking here, what attacks here? This thing attacks here. Right? Slap my hand. Sorry, you didn't even move. The other chlorine is much closer to the plus. And when it back bonds, what do you get? Well, this bond is forward. And when it back bonds, how's that bond going to be?
Backwards.
Backwards to get back.
No, it can't be. Here we go. Here's the plane. Here's the chlorine that's forward. This finger needs to bond to the paper. What bonds are forward? Half arm is forward, the other half arm is forward. How is this going to bond from the back over here? A boomerang? It ain't going to do a boomerang. Okay, here we go. I bonded to you. Now you back bond to the paper. The other hand. See how both bonds are on the same side? Now instead I want you to make your bond come out this way. Wouldn't it be easier just to bond from the same side? Yeah. Okay? If this chlorine's forward, the new bond's going to be forward. It ain't going to throw a boomerang bond. It can't reach behind there. Okay? And you end up with this. And that's not really an intermediate. Inserted. This. Then the chloride attacks. Let's attack here. Now how do you attack a carbon that has something bonded to it? Only backside. And this comes in backside and kicks that off. That remains bolded, but this new bond is what? Back. And that gives which one of these two here? It gives only that one. And that one ain't formed. And the difference here is, if you attack a free carbocation, you would get both. But apparently that's not the mechanism, because we know you don't get both. Instead, and this makes sense, doesn't it make sense that this is going to be attracting more of that plus? Yes, it makes sense. And we know from many other information that when you attack a carbon that's something bonded to it, you only attack the backside. Okay? It's like this. You're going to attack and kick something off. Instead of a free carbocation, attack and kick it off. Sorry, the group just blocked you. Okay? There we go. Which side can you attack? Try that side. Try this side first. Sorry, the group blocked you. How about, oh, free access back there. Okay? One side is blocked by the existing group, so you attack the other side. Bam, kick me off. Back side. We'll say more. See, the front is blocked. Here we go. There's chlorine here. You're going to attack that carbon. Isn't coming from behind the board better? And then boom, kick me off. But here when it gets kicked off, it's still bonded down here, and so it's not really gone. That's how we know. Chloronium ions have also been isolated. There's a paper down there if you want to look it up. Okay. So I'll let you chew on that for a little while. Next reaction. Okay. I may have to be out next Friday. Because of that, I've done a video for material. And 3 reactions in this handout are covered by video only. I posted that yesterday. And that will be the, what color is our outline?
Green.
Green. Where are we at right now? We're ready to do 2 addition of halogen and water at the top. Okay. Down here, 5, 6, and below video only. Okay. I posted that yesterday. Let's get to there. Number 2, addition of halogen and water. Question?
Yes, sir. On the previous one, why can't we just use the rationale that if a carbocation was formed, that of course the chlorine wouldn't be cis because they would interact more, whereas if they're trans, they would have less interactions.
You're just saying the trans product is more stable, and so the transition state leading to it would be lower?
Right. So that would make more sense than making a triangle, kicking people off. I mean, I guess if that's how it works, that's how it works. But I'm just saying the rationale.
There's many other reasons for that not being the case. Basically, you're making an argument that seems reasonable, but there's lots of other data that were
Sure.
and we don't have time to explain all the data, and we may as we go along. Right here in 5 seconds, I can't give you.
Understood.
Okay. Basically, what we're looking at is the theory. Okay. You got to keep in mind that many things we look at are theory, and the theory is supported by the most evidence. That's why it's the leading theory. And you can always argue, question things. If you have a reasonable, like, hey, how about this? That's great. Then let's start talking about the evidence, and let's see why this is supported more by the evidence.
Understood.
We just don't have time to get into all the evidence right here on the spot. But as we go along, maybe we will see more. At some point, because of the confines of just the 50-minute here, and we have to just sort of present the material. This is how it is. But it's up to you as much as you want to chew on it, ask questions, and go as deep as you want to get the understanding you want. So in the end, good, but we have to keep up the pace and move ahead. Formation of trans halohydrons. This is going to be a reaction with like bromine and water, chlorine and water. If you add the water, you get a different product. And you get a product that has 1 halogen and then an OH. There's the halogen there, and the OH is like we kind of hydrated it. And that's where the hydrogen comes from. It's called halohydrin. All right? And so how do we get this product? Well, alkenes don't react with pure water, skin of the apple, right? But they will react with the schizophrenic chlorine or bromine. And so the question at the very beginning was, why does the electrons attack the chlorine? Well, they don't attack everything. Electrons will not attack water. It's not reactive enough. It's not positive enough for the electrons to attack. But the chlorine is schizophrenic, okay, very polarizable, and it can attack it. And we can attack. Where are you going to make cation, left or right? On the left, correct? New bond to chlorine, positive. Is this really formed, or is something going to happen immediately? When the new group has a lone pair, and we'll see others, it's going to immediately back bond. And this is concerted. That's NAF. I'm probably not going to do this again, but the first intermediate here is what? Chloronium ion, yeah? First intermediate, just like before. And we do have a Cl minus right here. We should show that. Just like before. And before, this attacked here and kicked that off, and you got a dichloride. Dihalide. We didn't say dihalide before, but I'm sure it was in the heading. That's what you get. You're making a dihalide in lab this week, right? Okay? But in this case, if water is present, it will attack instead. And usually if you have water, you also use more water, and so it's also in excess. And this should be bonded here. And so water attacks here. Which carbons are going to attack, left or right? It's the same as if it was here. It's like why I like showing this for me. I mean, your answer is here. You just have to know that it's not going to attack a free carbocation. Instead, it attacks something that has this thing back bonded to it. And so now we have different stereochemistry we know is going to occur. And this attacks here and does what? Kicks that back off. And what does that give? And by the way, what else is formed here? Let's see if we can show that as a full molecule that's formed here. Let's see here. Chlorine comes here. Two methyls. And what's bonded here? Oxygen, right? And how many H's on the O? One. No, there's two right here. Did someone say one?
I skipped a step.
Uh-huh. Thanks for doing that. So now I can tell you not to do it. Because every mechanism step comes from arrows. What does this mean? Oxygen may bond to carbon. Well, we show it. H's don't disappear. And the other lone pair doesn't disappear. One lone pair may bond to carbon. That's it. But guess what? That's a positive charge. Does everybody agree that my mechanism arrows give that? Now, of course, how many lone pairs on this? Where did the third lone pair come from? These bonding electrons moved on to the Cl. Okay, I'm going to stop saying all this because it's standard arrow movement. All right. Products typically want to go neutral. How can we go neutral here? This lose an H. We also see we need to lose an H. What can take an H? You see this guy? Okay, it's not going to attack, but it can act as a base. Take the H. These stay behind. What is that going to give? When that stays behind, we have two lone pairs now, right? Plus what? What do we form here? This reaction is going to produce HCl. And we see that from our mechanism. And if you had some pH paper, it would, as this reaction proceeded, it would turn the pH paper red. Yeah? Now, you could use water to take the H. If I used another water molecule to take the H, and again, there is excess water, I would have produced what? H3O plus, and the Cl minus, okay, you can write up here, or H3O plus Cl minus. You could just end it like that. But how does HCl exist in water? Doesn't it exist like that? So if you did this, you would actually be more correct. But as I said before, I like to form actual discrete molecules. Okay? So I'll use the conjugate base to take H's instead of water when water is present, right? And so we see, it's the same thing. What's the difference here? It's just water attacks instead of the other halide. But if water attacks, you've got to lose an H. And so it requires a second step, or another step. And water attacking, we've seen this before, that was analogous to hydration. But over there, water attacked the carbocation. Here, water is attacking the carbon backside and kicking off the leaving group. Question?
So is the dichloride product still possible with this reaction?
Theoretically, yes, but if water's there, that's always going to be the product. Water will react. If you want the dichloride, keep it dry. If you add water, it's going to end up reacting and giving you a halohydrin. Okay, stereochemistry. What if we did this with bromine and water? This would have stereochemistry to consider. It's also got regiochemistry. You're going to end up with two things bonded to the alkene carbon. Is the bromine going to be on top or bottom? Top.
Top.
Well, think mechanistically. Where are you going to leave cation when this attacks it? Top. What does it attack? Attacks bromine, right? Not water. This attacks bromine. And we get carbocation at the top. And this can attack. I'll show it back. This could also be forward. Because an alkene is planar. Okay? Depends on the reagent. Here's the board. Bromine can be over here. The bromine's over here. It's going to attack the bromine bond. Carbon-bromine bond will be this way. But guess what? The bromine can also be over here. And if it's over here, the bond's going to be over here. And when you got 1 billion molecules, there's going to be the same amount of bromine on each side. Within 1 or 2 sig figs, 50-50. Okay? And if you go out to 20 sig figs, you might get a little different. Right? That's why it's both sides. Okay? Depends on where the bromine is. Because when you got a flask and it's stirring and everything, is it reasonable for all the bromine to be on this side of the alkene? No. It's going to be on both sides. That's why you get attacked there. But let's say you got attacked back. But doesn't this back bond? When it back bonds, this is back. How's this other bond now? Back. Has to be, unless it's going to throw a boomerang. Right? And this is actually forward. Okay? Right? This is NAF. Everybody agree?
Yes, sir.
Back bonding happens at the same time. Here's our bromonium ion. Right stereochemistry. What attacks here? Water? Which carbon does it attack? Top or bottom? The answer is over here. It's the same place you would make a carbocation. You just attack it here. This bond is back, so how's the new bond going to be from the water? Forward, opposite, backside. Don't confuse backside with always being back. Backside really means opposite side. Opposite the existing bond. If the one you're kicking off is back, this is coming in from the front. Okay? And we see, I'm not going to do complete mechanism, but that's why the OH is forward and the bromine is back. Br and H are trans because of the backside attack here. The bromine is back, the OH is going to be forward. Trans, and so it's a trans addition, anti or trans. These are sort of synonyms. Addition of the HOX across the pi bond. Question?
Why did he not switch back?
They got pushed the other way. You're going to kick off the red, okay? You're going to kick it off. How are you going to attack this?
Backside.
Backside. No, that's front side. Backside would be right here. Right behind it. Okay, here we go. I'll kick it off. Boom. This methyl is this way. When this comes in, okay, this comes in and this gets kicked off. Boom, it got kicked off. That's a bad bonding. What happens is this moves this way. It occupies more of that space. Pretend it's over there and it's going to get kicked off. It's going to, as this comes in, this gets kicked off. Okay? Boom, kicked off. This moves to make room. The existing group has to move. That's what happened there. We'll see more of that going forward. We're mixing in stereochemistry here, but that's coming up. But I do mix it in as we go because I feel like we should learn it correctly as we go along. Okay, you're also going to get an algebra. That's where everything is switched. Okay. There's probably a number of questions here. At the end of the day, if you do your mechanism and you understand different ways to attack carbons, which is explained here on this very important sheet, then you're going to get the right answer, most likely, if you just work through it. And all these details will just fall into place. Okay? So don't try to learn every little tiny detail. You learn the process, and the details will be there. Because they come from the process. Okay, predict products down here. Show stereochemistry when needed. Next, synthesis of epoxides. An epoxide is a three-membered ring with one oxygen. It's a cyclic ether. And these can be isolated and made. Okay? Epoxides are made by reacting alkene with a peroxy acid. 3 oxygens. And if you show out a structure with this, it's got 2 oxygens bonded. That's a peroxide. If that was an H there, that'd be hydrogen peroxide. Peroxide is bonded to a carbonyl, and it's almost like a carboxylic acid. It's called a peroxy acid. Most common one is MCPBA, metachloroperoxybenzoic acid. Should be in your book. We'll try to finish up here. I'll go through it real quickly. We'll begin here on Monday again. Okay. The reagent, 2 oxygens, very similar to 2 chlorines. This is polarized though, because of the carbonyl here. This N oxygen's partial plus. Alkene attacks partial plus. Where are you going to make cation at, left or right? On the left. Okay. We made bond to oxygen. We kicked off the other. Is this going to form, or is this going to back bond? Back bond. When it back bonds, what do you get? 3-membered ring. Got an H here. This looks like a bromonium ion, yeah? Chloronium ion. The difference is the oxygen can go neutral by losing an H. If that was a chlorine, there would be no H there. Since there's an H there, we can go neutral. And the thing that got kicked off right here, everything's shown by mechanism. It's actually like an acetate. It can take the H, leave the electrons behind, and that gives final product. And then, so the ring is not opened up. The ring remains as the product. And these can be made. See, the bromonium ion, this is going to react because it wants to open up so it can become neutral. These have been isolated, but they're very hard to isolate. typically it will react by a nucleophile coming in here and kicking that off. This is more, you can isolate this. Epoxides can be made. But do you see the similarity in the mechanism? See the consistency? You just have a different reagent. Okay, look through this. Try to work questions below, and we'll try to pull this together, and we'll be moving on. Okay? Everybody get a handout today? Are there any extras? That's a puzzle for practicing your alkene reactions. Okay? Take a look at it. I'll mention it another time. It's a riddle. How is the alkene able to learn all of its electrophilic reactions? And you get the answer by filling in the right answers to the questions. Okay?
Can you say after class the question?
Yeah, I'll be here. Yeah. See some of you in lab this afternoon. Recrystallization worksheet due Monday in class.